Yeah, I just want to play session chair and say something like
Sure, of
I'm going to
course.
hear a talk from Wrenna Robson about permutations, not permutations of the schedule. We just heard that. That wasn't part of the talk. I I looked into permutations of bitvectors. The best one I found was best victor. I'm not sure if the talk is going that direction or if there are other
Right.
kind of permutations we're looking into. And with that, take it off.
Super. Just to give you a little bit of context, I am a PhD student at Royal Holloway. I'm sort of in the cryptography. I kind of work in cryptography and verification of cryptography, which is kind of my interest in this. But this is going to be a low cryptography talk. So if you're suddenly panicking and thinking, I last learned about cryptography when I did RSA in undergraduate, and that's about it. Stick it. It's not going to be too relevant. Um, for the last little while, actually at the moment I'm writing on my thesis, which is a very joyful process that's not full of stress at all, as I'm sure you're all aware. But for the last little while, I've been doing some work formalizing a particular aspect of uh, a particular cryptographic design. That cryptographic design happens to be called classic Metal East, but I'm trying not to like jargon at you too much. It's a post-quantum cryptography scheme. And it has a particular element of it is that at some point you need to apply a permutation, but you sort of need to apply that in certain secure ways. And so there is a particular method it goes about doing this, and there is already a paper by one of the authors, Daniel Bernstein, which formalizes some aspects of that design. And basically, what I have done in my work is extended what Dan has done there and implemented it in Lean 4. And actually, is actually executable. So in some sense, the program that Lean 4 spits out, however inefficient it is actually verified by, it has all the nice properties and so forth. And in the course of this, I sort of ended up, as inevitably the way when you do this kind of cross-cutting project, when you're not like working on a particular area of maths, but you're doing some applied thing, you end up realizing and you need a bunch of stuff that we don't technically have in math level. So along the way, I ended up sort of proving a bunch of stuff and so forth. So I wanted to, first of all, in my presentation, give you a bit of an introduction to the topic, so you have some context, and then I wanted to sort of talk through my code, not in too much grievous amounts of detail, but enough to give you a kind of flavor of how stuff went. And I kind of want to talk a bit about from a lean and a kind of method head point of view, what I found easy, what I've done that I now need to get into math at some point, and kind of the perspective of how I went about doing all this. So here is the problem we're looking at. It to be clear, it's not like a problem I've solved. It has a well-known solution, but we kind of want fast, verified ways of computing it, and that's the motivation here. So I have some permutation pi on s to the n plus 1. So basically, bit vectors, if you like, of length m plus 1. Actually, the original paper does it for bit vectors of length m, but that's really annoying because when m is 0, you have to do a bunch of special cases. So I just changed it. I just changed that to m plus 1. Actually, I suppose for this bit, it could be any length permutation, but we are going to do powers of 2. And I have many secret arrays of that length. And I want to apply the permutation to my arrays. I want to send the 0th element to, or rather, I almost said that the wrong way around. I want to send my list to a list where the 0th element is the pi0th element of the original list, which is of course different from sending the 0th element of the list to the pi0th place. Actually, that would be like applying the inverse. I found when I was first getting to go through this, I made that mistake all the time. I still do it on occasion. Okay, so that feels fairly easy, but and this is kind of where the security aspect comes in. This is why it's important to understand this context. I want to do this in a way that an outside observer couldn't detect my secrets through side channels by like timing. We sort of assume nowadays that in theory, an observer might be able to time how long memory accesses are taking me, or just time how long a program takes to execute. So the reason that's a problem, right, is it means when I'm okay. So the naive way I might do a permutation is to have some kind of lookup table. But if I start looking up stuff based on secret values or whatever, that might have problems. And I don't want it to be the same length of time no matter what my list is. So I can't really do anything clever in terms of the values of my list. I want a constant time way of doing this rearrangement. And I want to do this reasonably efficiently, because actually, as it happens, basically, applying this permutation is going to be a key part of doing some kind of public key encryption. So we imagine that there's some devices somewhere doing it a lot all the time. So we don't really want it to be a really computationally heavy thing. So the idea is we want to do a one-off calculation on our permutation, which we are going to let be a bit expensive if we want, because it's going to be, we're essentially going to do that when we compute our public key, but not every time we do an encryption. And then having done that calculation, that will sort of produce the means to apply my permutation in a constant time manner, kind of arbitrarily, and we won't have to worry about this thing. So lean, obviously, with our mathlib heads on, what is a permutation? Well, it's obviously two bits of data, two functions, specifically from a type to a type, to itself, along with some proof that it's a left and right inverse of each other. It's a special case of an equivalence. Great. So is that okay? But like, is that realistic as a model for what a permutation is here? I mean, like, I feel like if you ask many computer scientists what a permutation is, they'll be like, well, it's a list of numbers which are all different, and it's a rearrangement of 0 to n minus 1 or something like that. So your problem, so you're kind of naively, right? You feel like it should be easy to look up the permutation, but like, how can I get the inverse for free as well? Which is what happens with lean, right? But not so much this. So is it fair to ask for that? Also, we can apply our permutation to a value, but like, if we're applying that to a value that is secret, then that might be a problem. So while we're going to develop this one-off calculation, I want to justify some stuff first, that it's actually going to be okay to do things like taking inverse or applying our permutation expensively in the course of producing this inexpensive means. So what you can do, this actually isn't relevant to what I verified, but it's sort of worth. It's the context of actually, how do you get around this problem? I think it's important to know. So if you consider the pairs pi I, actually I could form a whole list of those, or indeed pi I AI. What happens if I sort those lexigraphically? So sort pi I by the first coordinate, where I is our numbers, which are, I guess, the thing that my pi is my permutation is indexing. So it takes a little bit of time. You might need to think about this, but it shouldn't take too long to convince yourself that pi I, once it's sorted, will get sent to a list where the coordinates are I and pi inverse of I. As in, the 0th element will be 0. Obviously, that's where it should go at the end, because we've done a sorting algorithm there. But then what is in the right there? Well, it's whatever. What had 0 in the first coordinate, well, that was whatever, well, in the second coordinate, so that's whatever would have been mapped to 0 by pi, which is exactly pi inverse of 0. Okay, fine. And by an extension of this idea, we can get I a of pi inverse of I nicely. And then if we actually you sort of extend this again, or sort of do it again and search pi inverse of I, we'd get I a pi I. So in other words, like, if we can do sorting in constant time, even if it's expensive, we can do perhaps expensive applying of permutations, and that we're going to use that subsequently to actually find our cheaper way of doing permutations. And actually, these methods are going to have something to do with one another, or they're going to feel a bit similar. But basically, use something called a sorting network, which you may or may not have heard of. I don't know. So it's built out of comparators. So basically, the idea is kind of the basic thing I should be able to do if I'm sorting anything, right, is that you give me 2 elements, and then I spit out a pair of elements PQ, and I should be able to spit out the pair min PQ, max PQ. And crucially, I should be able to spit that out without an outside observer being able to detect which branch I took there. Can I do that? Yes. So as long as P and Q are something like a bit vector, or something you can do like masking style operations with, there is a way to do this. You basically do some cunning nonsense with bit shifting and masking and stuff, and it all works out. You sort of you do your comparison, but you don't actually do a branch, crucially, and that means an attacker can't really detect it. So you can do a basic, okay, I can sort 2 elements, and then what you do is you sort of go, okay, I'm gonna build a network of such comparisons where I'll sort of compare the first two elements and maybe flip them or maybe not, and then I'll compare the second two. And actually, it turns out if you pick the right pairs to compare in the right sort of order, then you can always guarantee that at the end of this, where you're always comparing the same pairs of elements in the same order, and so you're always doing the same operations, and you're never doing any branching, which means it's all constant time. At the end, you will have a sorted list, but you sort of never actually branched on anything. The fastest ways to do this are roughly OM squared. So I guess a square in the logarithm of the length of your list. So, and actually, the diagram a second, which will make this notion of a network a bit easier to see, because actually we use something similar in our doing a permutation, in our decomposition of our permutation. Because to remind you, although that has solved our problem of applying our permutation in constant time, it's relatively inefficient. So now what we're going to do is say, okay, well, I'm allowed to do that. So can I use that to sort of pre-compute enough stuff that I can then apply my permutation in a fairly efficient way? So yes, the answer is what you can do. So what we're going to do is we're going to sort of decompose our permutation on 2 to the n plus 1 elements into a series of stages. And basically, the first stage, I may or may not flip the first element, the 0th element, and the first element. Not because they're less or greater than anything, because we're not sourcing here. I just imagine I've got some kind of bit somewhere that tells me, and if it's 0, I flip it, and if it's 1, it's not. But and again, I can sort of do that flip without actually having an if-then statement, because I do some kind of bit masking thing. But the end result is that I can sort of guarantee taking the 0th element and the first element, I check some bit, and I can combine those together, and I have an optionally flipped pair. And then I take the second element and the third element and the 4th element and the 5th element, and so it's sort of adjacent pairs all the way down. Then on the next step, so that's if you think about it, 2 to the m flips overall. In the next stage, I'll look at the 0th element and the second element, so a gap of 2 now instead of a gap of 1, the first element and the third element, the 4th element and the 6th element, and so on and so forth. So a gap of 2 all the way down, and that'll still be 2 to the m flips. And I go all the way along until I've got the biggest possible gap that I could have in this regard, so doubling each time. So I may or may not flip, depending on what my big list of bits says, 0 and 2 to the m. And I go all the way down, and then I'm going to do that backwards, so making my gaps get smaller again until I sort of have a succession of optional flips between adjacent elements. And that means this whole process has had 2 to the m plus 1 stages, and each stage had 2 to the m flips, possibly flips, and I need a bit to control each of those. So this whole thing is controlled by 2 to the m plus 1 times 2 to the m bits. And it basically turns out, having calculated these control bits, which is a decomposition of my permutation basically into sort of these product of involutions, where those involutions are all products of disjoint transpositions, if you like, then that will solve the problem. I didn't write it here, but it's going to give you a way of applying your permutation in OM instead of OM squared, so the log rather than the log squared of the my length of my thing. Actually, there's some ways to squeeze more efficiency out of all of this, but this is the way that Classical-East defines its control bits, so that's kind of the official one, and it's the big one that Dan have outlined in his little paper. So yeah, okay, so that's but I haven't said how I calculate these things. So here's our picture that I ripped from Dan's latest paper. I want to ask him at some point for the latex source, so I can put it in my thesis, hopefully, because it makes this diagram easier. So you can sort of hit. But what you've got to remember here is each of these kind of arrows might not. Each of these points where my things kind of go off to another one, they might not happen. They only happen if the relevant control bit says, "Oh, actually, I want you to flip them." Because so if you look at the first one here, I've got my first one, the 0th one and the first one, but which way do they come out of that? Well, it depends on the bit which flips. So I'm going to need, I need a way of calculating my bits. So the idea is, and this is the inductive perspective I promised. So kind of obviously, if m is 0, that is to say I'm looking at flipping 0 and 1, or either I flip that or I don't. Easy. And that's clearly one bit of information, right? So that's fine. And how do I identify that? I look what it does to 1, and if it sends 1 to 0, if pi of 1 is 0, then wow, that must be the flip. So it's basically that's exact pi of 1 equals 0 is precisely like the Boolean value that I need. That is my bit. Okay, but so that's my base case, but I'm going to have an inductive way of doing it. You can show that there exists a sequence of bits F and L, each of length 2 to the M. Those kind of are going to be our outer layers on the end and the beginning. How you calculate those, I'll maybe talk about a bit later, but the details of that are less important than the fact they actually exist. So these generate permutations F and L, which are involutions, which are sort of just a product of disjoint transpositions. But you can then write pi as F times M times L, M just being calculated by multiplying pi on the left by F and L. But you can then prove, and proving this is really the thing. I mean, it's the thing that Dan actually verifies, and it's the thing which is sort of a lot of work you do is to do. You can prove that the M you get by the right choice of F and L, the M you get is parity preserving. Why is this significant? Well, because it's parity preserving, so it permutes odd numbers and it permutes even numbers, but it never sends an odd to an even or even to an odd. You can sort of look at this as 2 permutations, one on the odds and one of the evens, of half the size. And then if I repeat the same process to those, which I'm sort of allowed to do by some kind of inductive argument, I'll get some control bits out of those. And although I have to do some rearranging and interleaving of those bits, and actually that does cause some issues in the actual formalization, I will assert that at this stage, you can deal with that nicely. And so you break down these smaller permutations based on how M acts on odd numbers and how M acts on even numbers, and from this you get the bits you want. Actually, there's multiple choices of F and L, but that's okay. You have to choose one way, I guess, so it's unambiguous. The particular way we choose here happens to always set the 0th bit of F to 0. I've sort of an engineering exercise that I never quite followed to the conclusion, but it's sort of pretty clear. There's some symmetry between like the XOR of F and L is the kind of invariant thing, and that's kind of where all the other values come from. But we make some particular choice. So yeah, so that's kind of what I just said, right? So I can split M into 2 permutations, ME and MO, and then we sort of proceed inductively. So what have I actually formalized, which is I suppose what you're here for. So Dan in his original paper, which was from a few years ago now, he does this in whole light. I originally did it in Lean 3 actually some time ago. It was sort of a half-assed effort. I mean, this was actually really when I was first getting to grips with Lean. I sort of did most of it, or I think I went slightly further than Dan's original one, but to be honest, if that original formalization, looking back now, I cringe a bit because it wasn't very good, but it was fine. But my kind of new formalization of it in Lean 4 it goes as far down and also much further because actually it links it to you have an actual implementation of these algorithms in Lean, and also a slightly subtle point. So first of all, this is an you can prove that this is an injective process at the very least. You're never going to get the same control bits out for multiple permutations. So I found some inverse for it. But actually, we want there to be more true than there is. That there is some inverse. We want it to be true that, like, when we reinterpret it as I explained, that is to say, going layer by layer, that works. That actually is a valid. That will then interpret as the valid permutation. That is actually more challenging, essentially because of all this interleaving you do when you do the inductive step. But you don't do that interleaving when you go layer by layer. Actually, that's the opposite of what you're doing. You're kind of not. It's although it's kind of inductive. There's some way you can approach this inductively in either case. You can sort of there's layers. There's more or less layers. But actually, then when we go to interpret our control bits, the inductiveness you're doing is in a slightly different way. And actually, this was I really thought I wasn't going to do it, and then a couple of months ago, I had some bright idea about I see it, right, which hopefully we'll get onto. But it was that was a real tricky bit, actually, in terms of the actual formalization. But I managed to do so. So I intend to now. That's what I've sort of done there is give you the kind of background of the maths. What I'd like to do now is sort of talk you through a good portion of the actual lean code with some digressions, probably into various bits, talking about things about various things in MathLib. But I want to ask two questions. First of all, how long have I got in terms of time? And secondly, does anyone have any questions about the actual about the stuff I've just talked about? Because this is the time I really want to answer it before we get into any actual lean code.
So I can answer the first question about the time. I think maybe 10 more minutes plus questions.
Fantastic.
Okay,
cool. Well, I can do that's sort of what I was anticipating. So I can do a run through of my code. Does anyone have any questions about the actual mathematics here, or computer science, or cryptography, or whatever exactly this is? I mean, the math here is not. I mean, it's just permutations. It's not particularly hard stuff, but it ends up being a little bit technical. Okay, so can you all see? Can you see that? Okay. Is that appearing fine?
Probably a bit small on some of the screens, but we can read it.
Sure. I can find a way to zoom in. Control. There we go. Okay, that should be slightly bigger. I definitely want to that one open. Okay, so I want to talk about how I sort of successfully went about this. I don't know why that's giving me red. It seems very worrying. Okay, fine. Whatever. I'll do that in a second. It was actually working a second ago. I don't know why it's now not control. Okay. Failed to write Olean no such file directory. Okay. I don't know why that happened. Fine. I'll assume if I hit lean with a stick, it'll mostly fix it. So kind of went about this. It was actually a comment by Eric, as an Eric Weiser, that sort of set me onto the right way to think about this, which was when I said you do all these kind of flipping stages, really what you're doing is sort of at each stage you're flipping elements which are identical, other than like one bit of their kind of bit vector of their number decomposition. So 0 and 1 flip because they're identical except for their least significant bit. Then 0 and 2 flip because they're identical apart from their second least significant bit, and so forth. So I needed some function and some API for splitting a number. And I didn't use our bitvec object, which there's been some great work recently to make that slightly more accessible. At that time, that was kind of going on. I didn't want to touch something that might be a bit unstable. But I needed a way of, if I've got fin 2 to the n plus 1, I need to sort of separate. I want some way of going, okay, well, I want to pull out a particular place of that. And also I want the rest of it, for which I use the word residuum. I'm not sure it's a real word, but I'm not sure it's a word people use in math much, but I needed some term for it, and there didn't seem to be an established one. But basically the number you get when you pull a number out of a bit vector and then squash together everything that's left. Because it was sort of clear to me that was how I would go about that was actually going to be the right thing to compare. But then obviously having defined such a thing, I mean, the nice thing was, and this is somewhere where I want to say this is where I think there was a real strength that we have with MathLib, is that all the equivalences and such are to define such a thing are already there. So that actually you can see my definition for it is fairly concise. And I think a real lesson of this versus sort of the approach I did when I was doing this very naively some years ago, a couple of years ago, or whatever it was now, is actually, when I have some equivalence or something which is going to be an equivalence, actually defining it as an equivalence. I feel like the naive approach, the thing that I see people do who are less used to formalization, is to just define a function and then define another function and then prove those functions are inverses. And you can sort of avoid doing that if you just prove it to, if you can put a bunch of equivalences together using the tool we already have to do that, it just all works TM. So I would say that was a key lesson. I don't know why this is taking so long to launch. I assume because I'm streaming. Okay, so most of this file was doing this. I will say that at one this was sort of the source of my first really tricky thing. Actually, in the end, I found a way to sort of get around it. But you might want to think about you don't need to worry about the code so much, but like sort of intuitively, I might say something like, well, if I take a bit out of a binary string and then take another bit out of that binary string, then on some level, if I do that in the opposite order, that is to say, take the second bit out first and the first bit out second, whatever exactly that means, that should give me the same ultimate result. And actually, you need this in practice to prove things like actually, when you're proving things like kind of bit invariance, which is the generalization of this notion of parity preserving, in some sense, if I've got something that flips a particular bit, then clearly it's not going to flip the rest of the bits. But actually, it turns out to really express things like that. You need some decent or sort of related things. You need some decent understanding of this order thing. To do that, you need a bunch of theorems about, or you need some certain theorems about suck above and pred above, library functions we have for fin, and we didn't have them. And actually, they were really annoying to prove. And then I ended up getting distracted, as one does with Lean, and it took me ages to do. But I found a better approach to them. As it happens, we sort of had them, or had something very close to them that was for which they were a corollary, but they were in the simplicial categories file. Because that's actually they turn out to be. It turns out what I wanted was the first simplicial identity. I didn't know this, but we didn't have it in a more simple form. So, and I currently have quite a radical PR that reforms a bunch of suck above kind of based on this. I suppose I'm mentioning this because it's sort of like it's a good example of you can be driving along nicely, everything's hunky dory, or using massive functions fine, and then you suddenly find somewhere where no one's quite had to do something in a certain way before, and then suddenly you're like and that can be quite a jarring process. I mean, it's sort of fine for me, and I kind of know how to negotiate with stuff. But it's I was sort of reflecting on for the average MathLib user who might not be particularly engaged with the community, whoever wants to use it for actual stuff, how they then engage with the community to kind of get help with that, and that can be really challenging. I mean, what I really tried to, and the other example that I want to say is, so we have over in the kind of submonoids, we have this construction, given some type, which is a monoid, I can form M cross, which is the type of units of that monoid. And that's sort of fine. But if I have a submonoid of that monoid, then I sort of clearly have a subgroup of its group of units, right? We didn't have that subgroup. We have clearly, if you have a submonoid, then considering that as a type, you can form a type of units. But there is a subgroup of the units thing we sort of just didn't have. And actually, it turns out there's some nice Galois co-insertion that exists between this and coercing a group of units to a subgroup of units to a submonoid of the original thing, which I then went and proved. I've got a PR out at the moment that does this, and I sort of needed this because basically it's at a certain point I mentioned I'd finally solved this difficult problem. It all came down to realizing this equivalence that exists between if I've got something parity preserving, it splits into an even one and it splits into an odd one. Well, yes, it certainly does split, but it's more than it splits. That's a homomorphism, and actually that was exactly the thing that I needed to be true. And that was again somewhere where the sophisticated ways we have in MATLAB of expressing stuff meant I didn't really have to, once I realized what I needed to prove and the things I needed to be true, I could just sort of put stuff together and define instances of stuff, and it all sort of came together. But then I think if I suppose the point I wanted to make to you all as a group is not necessarily the particular details of this. I kind of have to wrap up on that now. So I wanted to mention those two in particular, but I think it is really challenging it could be really challenging for someone who wants to use MathLib to sort of know what to do when they find something that's missing. I mean, clearly they might. I mean, I think they should be. I strongly believe in a culture of and a lot of my stuff I've factored out so that it will be easy to parcel up into PRs, some of which I've pushed already, some of which will probably happen in the future, because I think there's some utility to them in general. But I think the pathway for future people who will pick up MathLib will prove things that are useful to push those back into MathLib and become something that other people can do and use in their projects. I feel like if you're really engaged with MathLib and Lean as a project and as a sort of community in and of itself, you will do that. But if you're not in that position, and I have seen people not in that position who sort of do this, then what you'll probably do is write your code in a way where it's all focused towards getting to your goal, but thinking about with a MathLib head on about the right generalizations, the right way of structuring stuff, and knowing how to file the PR in the right way so that it will kind of actually get into MathLib, and ultimately that's something that we should be encouraging, because there probably will be these little edge cases that people find with us. There's a useful thing or a thing that they found useful that some other person would find useful, and we really don't want them to repeat that labor. And the pathway in is not necessarily clear. So I guess that's kind of what I wanted to end on from my point of view. Is this was a project. It's gone quite well in terms of the formalization in Lean, but those are some takeaways I had about not necessarily my experience, but certainly the experience I could see someone who hadn't had as much of a prior engagement with a massive community as I've had, if they had done. Yeah, okay. Sorry, I know I went slightly over time. Do people have any questions?
Yeah, thanks for that. I think we have time for like 1 or 2 questions, and then I would recommend everybody join the gather space, because I made some good points about MathLib interaction, and I'm sure there will be a good discussion following from that. But let's see right now.
I'm interested. Yeah, Keith has disappeared. I don't know if he just decided he couldn't take any more. But yeah, I'm happy to answer any questions people have.
So if there aren't any from the audience, I guess as a member of the FRO, what I hear is that you might have some comments on like MathLib, but Lean was great.
Yeah. Actually, and I really want to emphasize that I think I like the emphasis in Lean 4 as a programming language, a thing for doing stuff. I mean, I felt a lot more confident programming a thing to do this. I don't think I did it in the best possible way, but I mean, I've been quite an advocate for Lean in the cryptography community, where it's not really, I feel like there's not loads of it about at the moment, because I'm like, well, actually, I think we really should be looking at this stuff. I think there's a lot of interest. There's some interest. I feel like Coq is more standard in some ways, but I feel like the idea that you can there are other languages out there that do, you know, I can do fast execution, but hey, also I can verify stuff about it. But I find Lean really easy to use. I think Lean 4 is in general a big improvement. Yeah, it's really fun. I mean, I'm glad I found an excuse to spend a bunch of my PhD time doing some Lean stuff, because it's fun. And I have to say, having tried a bunch of other verification tools, that isn't true of all of them. And I think there is, I think one of Lean's strengths as well as its technical merits. And I mean Lean as well as MathLib, because I think, you know, there is clear engagement from users, from the FRO. You know, there's people who are interested and want to help people, and that makes such a big difference. It really is. It's one of the big strengths is that you have kind of little conferences like this and things like that. There was an interest all the way down.
That's a great ending note for the program of this day, I would say.